Welcome, Doug. Good to have you today.
Thank you, Maury. I appreciate it. Well, welcome. Good morning to everybody. LEDs Magazine, I want to thank you guys. I also want to thank our co-sponsor, Digi-Key. Again, my name is Doug Rooks. I am the Field Applications Director for North America, supporting the West. LEDs Magazine came to us and wanted us to talk about LED component selection. So there's a lot of different options out there, and typically you're trying to get to market pretty quickly, and there's a lot of different types of applications. So introduction, purpose of this, provide an overview of LED components, including review of the different LED types, from through-hole to high power, discuss the decisions when choosing an LED. I was really trying to be LED agnostic, so from a manufacturer standpoint. So there's pictures of LEDs from Seoul, there's pictures of LEDs from other competitors. The specifications are kind of across the board depending on what types of products we're looking at. So this picture kind of shows the different types of LEDs that are out there. There's the old through-hole type, there's the high flux, there's the chip LEDs, and then there's some side view type products from that top line. Really not going to focus on these types of products. Really going to focus more on general lighting application type products, but I'll talk a little bit about them. Then we move on to mid-power type of LEDs. These are going to range from about 0.1 watt up to about a watt. High voltage and AC LEDs we'll talk a little bit about. High power and super high power LEDs. So let's talk a little bit about low power briefly. So again, these are your through-hole, high flux, chip LEDs, side view type products. Most of these are older types except for the side view. Side view is typically going to be used in your backlighting type applications for small displays like your cell phones, laptop displays. The other products are really for keyboard or button illumination and indicator types. But these again are less than 0.1 watts and typically pretty low flux output. So if we move to mid-power types of products, the specs on these are going to go from about 0.1 watt to 1 watt. I believe Strategies Unlimited actually says 0.1 to 0.5, but for this presentation I'm going to use 0.1 to 1 watt. Specifications are typically around 15 lumens to 100 lumens. The package densities, 5.5 lumens per millimeter squared up to about 12 lumens per millimeter squared. And again, the specs change pretty quickly. So this is just kind of a snapshot of what's kind of out on the market right now. If you look at most mid-power LEDs, most of these are going to be flat tops. They're not going to have a dome on top for the most part. And we'll talk a little bit about that, what the reason to use a dome or a flat top is here in a little bit. Can be good lumens per dollar, actually very good lumens per dollar, and or good lumens per watt. Moving on to high power, these are going to be your 1 watt to 5 watt types of packages. I've shown some of our LEDs here on the right-hand side. Some of these are 5 watt at typical current, but you can drive them higher and actually get into your super high power up to about 10 watts. These are going to range approximately 52 lumens per millimeter squared from a density perspective. Typically, most of these are going to have a dome on top of these. I'm showing the Z6 here, which has a flat top on the right-hand side there. This is our RGB plus white package. These are typically going to be very high lumens in a small package, so if you need a lot of light in a small area. So moving on to super high power LEDs, the specs on these are going to be anywhere from 5 watt and up. I think the highest power that I've seen out there is about a 120 watt package. It's going to range anywhere from approximately 500 lumens up to 12,000 lumens. Package density is going to be about 42 lumens per millimeter squared, so it's actually a little bit less dense than what your high power packages are. These consist of multiple large die packages. So I've got our P7 on the left, one of our older products. The Z7 is the newer version, and then the Z6, which is the RGB plus white. And these are typically going to be 1 millimeter by 1 millimeter multiple die in a package or larger. Then you have like chip-on-board type products. These are multiple small dies in a large package. It's going to be very high lumens in a small area. Let's talk a little bit about high voltage and AC LEDs. So really the difference between an AC LED and a high voltage LED is AC LEDs had die in both directions, right? So on the positive side of the AC wave, one string was on. The negative side, the other string was on. These are going to range anywhere from about 0.3 watts up to about 8.4 watts. They're going to range in voltage anywhere from approximately 12 volts up to 100 volts. We are calling our products multi-junction technology products. There's no wire bonds connecting the die. It's actually put onto a metallized sublayer. It's a monolithic array of LED cells. Our products typically consist of 13 volt at about 0.3 watt, 22 volt at 0.44 watts. We also have a 32.5 watt at 1.2 watts, a 62.5 volt at 1.4 watts. So depending on the application, what you're trying to do, multiple configurations there. These are going to range in lumen output anywhere from approximately 30 lumens up to 900 lumens. Actually, Seoul Semiconductor had AC LEDs. We were the first generation of AC LEDs out there about 4 years ago. Most of our products now are just high voltage, or we're calling them multi-junction technology. There are AC LEDs out there nowadays still. Our strategy is actually to move forward to just a series in one direction. Because if you think about it, when you're driving them with an AC wave, half the die are on, or half the die are on, and half the die are off. So you're kind of wasting half the die. So you can get smaller packages and lower the cost by going to a string in one direction. So we've talked about the different types and styles of LEDs. Let's move into applications. There's a lot of different applications out there. I'm not going to go into a lot about the application. Just want to show you the different styles that are out there. LEDs can have a fit in multiple applications. One LED is probably not going to fit every application. You could even have the same application, depending on the customer and marketing. That LED may or may not be the same that they would use in the same application, depending on the requirements. So here's some downlights on the right-hand side. There's some cans on the lower right. There's some troffers. So some of them are small form factor with glow-on light. Troffers, you have a lot of room to play with, so you can really spread those LEDs out. Here's some outdoor applications. So we have street lights. Obviously, everybody's probably very familiar with those. Pole top or bollards, security and wall packs, high bay and low bay type products, spotlights. Something to think about with these is they may have a certain radiation pattern you want when you're shining it on a certain surface. You may want an oval pattern. You may want a circular pattern. So things to be aware of when you're looking at some of these types of products. So other applications, and this is kind of include a few different things. So really it's retrofit type products like your power lamps, your A lamps like A19s, linear modules, so under cabinet, cove lighting, can be troffer style linear lights. I threw in some decorative. I know that's not really general lighting, but I thought it looked cool. Landscape lighting. So there's a lot of different applications out there. So something to think about when you're picking the actual LED for the actual product you're going after. So moving on, and this is really decisions. So decisions. Really the two key criteria are at the top. You have your efficacy, which is lumens per watt, and then also your lumens per dollar. But a key factor in those numbers is really your temperature. What's your end application actually operating at? You also have density or size. So how many lumens do I need in a certain area, or lumens per millimeter squared? Directionality, what type of beam pattern do I want? Do I need a focus beam? Is it okay to spread the light? Depends. Talk about hotspots and distribution of the LEDs in a system. Do I care? Maybe, maybe not. So moving on to efficacy. Efficacy, I believe everybody's probably very aware of. It's your lumens per watt. This is the amount of light produced by a light source as a ratio of the amount of power consumed. Typically a very easy equation to work out based on the specifications of the data sheet. So I've taken just a snapshot of the data sheet, did the calculation here, it comes out to be about 138.7 lumens per watt. Now, we haven't looked at temperature yet. We haven't looked at drive current. This is based on typical current, and we'll talk a little bit about that as well as temperature here in a second. So at typical currents, LEDs which are being used in most general lighting applications can range anywhere from about 80 lumens per watt to 160 to 165 lumens per watt, at least what's out there nowadays. Most high-efficacy LEDs that we're seeing right now are the 0.2 watt or around there, 145 lumens per watt, and then 1 watt type packages which are ranging 160 to 165 lumens per watt at the high end. So you can get that, but you got to pay for it. Remember, if you underdrive an LED, the efficacy goes up, right? So you can actually play a little game with that, with your efficacy. Lumens per dollar. This is the amount of light produced by a light source as a ratio of the cost. And from an LED perspective, again, pretty easy calculation. Pull the data sheet up, pull the lumens out of it, know the price of the LED. With this one, you come out approximately 558.5 lumens per dollar. You may also see dollars per lumen, dollars per kilolumen, just an inverse ratio of lumens per dollar. At typical currents, LEDs which are being used in most general lighting applications can achieve up to approximately 780 lumens per dollar, which is very good right now. At this point in time, mid-power LEDs seem to get the best lumen per dollar, but high power can also achieve good lumens per dollar. Same with efficacy. If you can overdrive an LED, you can achieve higher lumens per dollar, but that's the inverse ratio of efficacy. So if you increase the current, you get better lumens per dollar, but worse efficacy, and vice versa. If you lower the current, you get better efficacy, but lower lumens per dollar in a system. So the temperature of a system. Reliability and performance of an LED is directly related to the junction temperature. Therefore, the better you can dissipate the heat, the longer and better performance you'll have in a system. This is going to affect your lumen maintenance as well as your flux output, therefore efficacy of a system. I took a snapshot of flux versus temperature here on the bottom left, so you can see how it directly relates. Flux drops off as temperature goes up. I also took a snapshot of a TM21 report on the right-hand side at 55 degrees C case, 85 and 100 degrees C case. And if you look closely at it, at 55 degrees C case, your L70 calculated is around 85,000 hours. But you jump to 85 degrees C, and you're going to see around 59,000 hours. So you can see how that directly correlates to the lumen maintenance as well as the flux and efficacy output of the LED itself and the system. So super high and high power LEDs typically have very high lumens in a small area, therefore can tend to be hotter than a mid-power LED. If you have the room, it may be better to go with a mid-power package to spread the heat out. This also may allow for the use of an FR4 board instead of a metal core PCB, which can lower the overall cost of the system. Density, size of a system. So how large is my fixture? How many lumens do I need? So really your lumens per millimeter squared. I have pictures here of multiple different products. There's the A19, there's MR16 type products. So I think most of us have gone to the local hardware store, Walmart, wherever, and they've seen 40 watt, 60 watt A19 replacements. The next big opportunity is going to be your 75 and 100 watt replacements. The hard part right now is being able to get a high enough efficacy LED to get the heat out, to get the lumens you need for that type of product. MR16 is the same way for the 50 watt replacement. Again, very small form factor. You got a lot of heat. It's very hard to get that out. So efficacy numbers are probably going to have to go up to meet some of those requirements. A troffer, obviously a very large fixture typically. You got a lot of room there. You can spread those LEDs out. You can spread that heat out, lower dissipation. So if you have the room, it may be better to go with a mid-power package, as this will allow you to spread the heat out and keep the temperature down. Mid-power packages also seem to be the best lumen per dollar option right now. But if you need a lot of light in a small area, chip-on boards, super high power, and power are going to be your best bet. So let's talk a little bit about directionality or radiation pattern, beam pattern. Do I need a specific beam pattern? Street lights, we typically have type 1 through type 5 beam patterns. Is it a spotlight? Is it a security light? So street lamps, PARs, MRs, security, and wall packs can and typically probably will have some type of beam pattern. I've shown a picture of a couple of different types of LEDs on the left-hand side of the page. There's what we call dome top and flat top. Typically, domes are going to work better with the secondary optic, so it allows you to focus that light a little bit better. As you can kind of see on the right-hand picture over there, you got the 3 LEDs, and you have a secondary optic on each one of those LEDs to focus specifically each of those LEDs in a system. So if you have a fixture which needs a specific beam pattern, LEDs with domes are typically going to allow for a more even light distribution where a second optic is used. Chip-on boards can also work in these applications if you just have a reflector on that. I've also thrown in some of the different types on the bottom right-hand side of street lamps for beam patterns. So type 1, type 2, type 3 are kind of elliptical. Type 4, all of the radiation patterns out in front of the lamp, none of it going behind. And then type 5 is more of a circular pattern. Hotspots, distribution of an LED in the system. Do I use a lot of low or mid-power type LEDs? Or do I use a few high-power LEDs? What about shadowing? I don't know if most of us have actually gone out and worked under a light where you have LEDs spaced out quite a ways in the system, and depending on how diffuse that lens is, if you're working underneath that light, you can get multiple shadows, which can make it very difficult to work sometimes. But I also have some pictures here of an A19 type bulb in the upper left-hand side. There's one that looks very nice, very clean light output, even light output. But then the one right next to it has multiple LEDs there that you can actually see. Well, is that good enough? Maybe. Most of the time, I'm not going to look directly at an A19 bulb. I'm going to be blinded. So it can depend really on marketing, what customer base you're going after. There's the troffer on the bottom left. Very even light output. Looks very nice and very clean. There's the top right, a linear light, which you can definitely see the LED spots. Is that good enough? Maybe. I think it depends on what application you're going after, what marketing is looking at, and it's really a lot about perception. So most often this can be all about perception. but something to think about. Typically, if you have the room and want a more even light output, mid-power LEDs are going to be the way to go. So in summary, what are efficacy and lumen dollar per needs? And those are typically going to allow you to narrow down the LEDs to look at. Don't forget about the heat. You need to understand what that is, because that's going to affect the lumen maintenance. It's going to affect the flux output and the efficacy of your system, as well as your lumens per dollar. How large is my fixture? How many lumens do I need? So lumens per millimeter squared. What type of radiation pattern do I need at the fixture level? Type 1, type 2, type 4, is it a spot? So these are all kind of things to think about with the design of your system. So thank you. Invite you to take a short survey to receive a free Acridge 2 4-watt module. This is using our high voltage Acridge MJT LEDs with our proprietary IC. It basically replaces your typical conventional power supply, which includes typically electrolytic capacitors that definitely don't have a long life and can reduce the system life of the product. So please take a look at the survey. Please answer some questions. Let us know what you think. I appreciate your time. I'm going to hand this back to Maury.
Thanks, Doug, and for a very good presentation. And for those of you in the audience, I just remind you, if you haven't asked a question yet, you can still do so. Just go to that Ask a Question area of your console and type it in and click Submit. Also, just a note about the survey will be pushed out to you right as we end the presentation today. So don't be surprised if you're not seeing it right now. But as the presentation, after we get through the Q&A session and we sign off, that's when the survey will be pushed to you, and you can fill it out to try and get one of those modules. So, Doug, you kind of started off talking about mid-power LEDs, and that's a relatively new topic for some people, because this person has or states in the past we've heard a lot about low power, low watt being less than 1 watt, and ask, is a mid-power a new category?
I don't know how long it's actually been defined. If you look at the latest Strategies Unlimited, it defines low power as less than 0.1 watt. Mid power is 0.1, I think, to half a watt, and then half a watt up to, I believe it's 5 watts high power, and then high power is 5 watts and up, or super high power is 5 watts and up. So it's relatively new, but there is a definition from Strategies Unlimited on that.
Yeah, I think we're seeing a little bit of, a little bit of difference of opinion from different makers about exactly where those limits are, but I think that's a general description.
Yeah.
This person asks, is it possible to have a 5-watt high-power chip working directly from a 12-volt DC supply?
A 5-watt chip working directly from a 120-volt supply?
No, a 12-volt DC supply.
Sure. I mean, shouldn't be any reason why that wouldn't work if you have a specific driver that's going to handle the voltage and current that it needs.
It just may be the case that you either need an LED with multiple emitters in the package, or either multiple LEDs to get to that kind of to that 12-volt forward voltage, right?
That's correct.
You talked about. You used the term MJT, which I think stands for multi-junction technology. Is that right?
That's correct. That's what we're terming basically our high voltage family of products. We've been doing. Yes, go ahead.
No, well, go ahead.
So yeah, we've been doing this for over 4 years now, and basically it's a monolithic array where we've grown all the dye up on one substrate, and then we pack it. We put those dye down on a metallized sublayer to connect each of those die, so you don't have your typical wire bond between the die, which a lot of people have done in the past. So it's a more reliable system.
So it's really there are a bunch of different ways to get at putting multiple die in a package, and And so that's the difference, if I understand you correctly, that what you mean is some people actually take separate die and actually run wire bonds along the top of the chip.
Correct.
Now, are your die already singulated when you put them down on this metallized substrate, or
it's actually developed. It's actually developed that way, so you kind of grow them as multiple die. So it's not setting multiple chips down on a package. You're actually growing it that way. So it's one monolithic chip now with multiple chips on it.
So there is no singulation of the die. It's actually the epitaxial is done that way, and then during etch and lithography is when you actually create that MJT technology.
Correct. And you can do multiple series, multiple parallel. So depending on what you're looking at, multiple voltages for different types of LEDs. Yes.
But you believe that's a more reliable, more robust way to get to multi-emitter type package?
Yes, we do.
And I have a specific question that says, are these non-wire bond mountings done via flip chip?
No.
The efficacy, this person says, the efficacies mentioned are highly dependent on drive current, temperature, and color temperature and CRI. And so you were talking about typical efficacies. When you mentioned those typical efficacies, what kind of conditions were you thinking of?
So it depends on the specification from the manufacturer. And obviously, it all depends on in-application requirements. But typical efficacy defined here is at the typical current, and on this one, it was 25 degrees C junction temperature. So that's the typical efficacies I was looking at. But again, it really depends. Are you running at lower current? You're going to get higher efficacy. You want higher current, lower efficacy, but better lumens per dollar. What temperature you're operating at. And you need to do kind of the equations and kind of calculate what that efficacy is in your end system. Does that describe the question?
I think so.
Okay.
Obviously, chip-on-board technology's been a very, very hot topic of late, and this person asks, could you talk a little bit more about using COB versus some of the new single-die, high-brightness LEDs? Where do you see the single die running out of steam?
That's a good question. I probably don't have a really good answer for you at this point in time on that question. I may have to kind of look into that a little more deeply.
Well, what could you talk about the optical trade-offs of say COB versus either MJT type or single die type LEDs?
So typically, when you have an application that requires a certain beam pattern, if you're going to use a secondary optic on top of it to focus that beam, a dome type package is going to give you a more even light output, where a flat top, and it really doesn't have to do with MJT LEDs, it's just the type of LED, whether it's a dome or a flat top. The flat top is not going to be as even light output, so it gives you the capability to really focus that light and have an even light output from that type of product. So it doesn't really matter whether it's MJT or not, it just has to do with the package style.
Okay. So you talked about overdriving LEDs and thermals and reliability. This question gets pretty directly to the point. How is reliability affected by level of power? Is the higher power less reliable and lower lifespan?
I wouldn't say higher power or less reliable. It's just you're going to have a lot more heat created in that package. So if you're able to figure out a way to dissipate that heat, if you're running a 5-watt LED and you're running a 1-watt LED and that junction temperature is the same, you're still going to have a very reliable system. But if you can't get that heat out of that 5-watt package and that 1-watt's running lower junction temperature, that 1-watt package is going to be more reliable. So it's really about getting the heat out of that LED.
And so, a couple of questions about how do you determine what is safe and what are the thermal requirements? And this particular question says, how do you Seoul Semiconductor specify for your chips what the max temperature with which they can operate, and what are the recommended guidelines for operating them?
It really depends on the type of LED in the package. We'll list typically a max junction temperature. On some of our modules we recommend a max case temperature for the board itself. Then you need to look really probably at LM80 and TM21 calculations with your operating temperature to understand what the lumen maintenance of that device is and if it fits your needs.
So you talked about the flat top and the dome LEDs, and mostly I think you talked more about optical, and I might have a question there, but this person wants to know, is there an efficacy trade-off between the flat and dome type?
That's a good question. Typically a dome type, you're going to extract the light a little bit better. But I mean, in flat type, I think I'm seeing 145 lumens per watt. In some of the dome types, I'm getting up to about 160. So it seems to be right now, the dome packages have a little bit better efficacy, and it does extract the light a little bit better. So there, yeah, they might be a little bit higher efficacy.
Is that due, do you think, to the optics, or maybe to the fact that most of the flat top are the kind of low to mid power devices, and perhaps maybe because those have been used in the past more in backlighting applications, might it be just the maturity of the technology for general lighting? And I don't know the answer to that, but or is it, you think, the optics that?
I personally believe it's the optic, the dome on the package that's going to give you that. Yeah, I can't think of anything else. I really think it's probably just the optic on top of there.
Well, this person's asking for a follow-on presentation on drivers. I don't know we can promise that today, but can you talk a little bit about the drivers needed for the kind of LEDs you covered, and maybe even a little bit, about you guys are in the driver IC business now as well.
Yeah. So good question. So yeah, there's a lot of different drivers out there today, a lot of different technologies. Do you want to design your own driver? Do you want to go out and buy a brick from somebody or a power supply from somebody else that's already done? There's a lot of different technologies to it. The manufacturers of the actual discrete regulators, DC switchers, have gotten a lot easier. There are a lot more app notes on them, so it makes it easier for customers to design them on their own. With typical conventional drivers or power supplies out there, though, typically you're going to have an inductor, you're going to have electrolytic capacitors, you're going to have your switching regulator in there. Electrolytic capacitors can go dry, and their typical life is going to be around 10 to 15,000 hours. So what we've come up with is an IC that will drive our multi-junction technology LEDs in a system that does not require your typical electrolytic capacitor in a system or your typical conventional driver. So it saves a lot of space, it reduces the thermals of the overall system, and its life is around 87,000 hours of life. So that's kind of what we're doing with our IC specifically. But again, as far as other drivers out there, there's a lot out there on the market. You can do your own. You can have somebody else do it. There's constant current. There's constant voltage. Typically recommended constant current to drive the LED because of the IV curve. But there's a lot of ways to do different things that you want to do out there.
You talked about AC LED a little bit, and kind of maybe there's a little bit of confusion between what an AC LED is and what a high voltage LED is, or even what an AC LED was a couple of years ago versus what it was now. Because I know you talked about what maybe was called anti-parallel. You have a string of LEDs in each direction, so you get them working on half waves of the AC main. And clearly, you talked about those being that being a case where you aren't really getting the most out of your LEDs because half of them are inactive at all times.
Right.
But AC LED, some people are still talking about AC LEDs with topologies that have gone beyond that. When you talk about your high voltage topology, is it one of these newer things that some people would be calling AC LEDs, or is it really something different entirely that just finds a different way to get rid of the electrolytic capacitor?
I mean, from an AC LED perspective, I consider an AC LED just really, as you put it, anti-parallel string of LEDs, so one in one direction, one in the other. I know they're working on adding different circuits to that configuration to make them more user-used, like our Acridge IC chip. But I think there's a lot of room to grow still in this arena. The technology is still pretty new. I mean, we've been doing it we've been doing high voltage /AC LEDs for over 4 years. Our IC's been out for probably over a year now. So I think there's still a lot of things that can change and improve the technology and what's called an AC LED that may change or morph over time what AC LED is called.
Yeah, I kind of like to think of it in terms of it just being another driver topology today, because it really and truly there was never an AC LED. There was an LED module, if you will, or a multi-chip package that you could drive via AC. So I would call AC drive just one more driver topology in the overall grouping of different driver topologies, you might say.
Very good point. Yep.
Here's the question. I don't know how you'll feel about it. In your experience, what do the Chinese Tier 3 high-power LED makers sacrifice in their manufacturing quality? They are super cheap, and I am very hesitant to use them. If I do, I want to know what I'm sacrificing or risking. Can you share your perspective?
I mean, my first one would probably be reliability. Make sure you understand the reliability of their product. Make sure you're looking at hopefully LM80 data and really understanding their product. Make sure you're testing it, doing over temperature testing, high current testing, run some tests, stress tests to make sure that it's going to be what you need. But just be very careful when you're looking at those products.
This, I guess, is a question really about your own ICs. Do all the parts in the presentation have LM80 data, and are you testing beyond the required 6,000 hours? Also, is this internal testing at Seoul, or is a third party doing the testing?
So, yeah, good question. All of our products that are for general lighting, which are mainly the ones we talked about today, have LM80 or are in test. We are an Indy Lab approved lab, certification lab, so we can do our own testing in-house. So we do some in-house. We have a limited number of temperature ovens, so we do some of it out-of-house as well. We are doing testing past 6,000 hours. We have some at 8,400 hours already. We're going to continue testing at least to 10,000 hours.
You've really touched off quite a lot of discussion in terms of questions about the Acridge 2 topology and the lack of electrolytic capacitors. One person wants to know, are you serious? No caps at all, and how does that increase reliability? Another person asks, is the rectification in half bridge or full bridge or some kind of fractional phase behavior? Some of that's even, I'm not quite sure about fractional phase behavior, but is there anything else you can share about what you guys have seen is perhaps what you believe is the optimal driver technology?
Right. So actually in some of the product information, the white papers that you guys have access to right now, it talks a lot more in detail about how the IC operates. Specifically, the latest one is what we call kind of a 4-step IC. So if you're operating at 120 volts, you have a step at 30 volts, you have a step at 60 volts, a step at 90, a step at 120. And it's actually a little bit less than that because the LEDs are going to turn on before that. It just makes it easier for calculations. But as far as reliability, electrolytic capacitors, 10 to 15,000 hours. I mean, you can overspec them. You can. You're typically going to pay for them. They're going to be larger. That's going to create a larger package size. As far as the frequency, we're operating at 120 hertz currently. So basically, we're doubling the 60 hertz waveform that's coming in North America. I think I answered all those questions. I believe.
Yeah,
I hope.
I think. There was a section that you talked about applications, and you talked about retrofit lamps. And obviously, in the short term, retrofit lamps are a very popular topic because a lot of people see that as the easiest way to deploy LED lighting today.
Sure.
And I think you made a good point that the next frontier being the 75 100 watt type replacements for A lamps, and maybe even more difficult, the MR16 lamps. Could you talk about that in a little more detail, and more specifically, I mean, how short are we in terms of efficacy to be able to really serve that MR16, say that 50 watt MR16 type retrofit, or the 100 watt type A lamp?
Yeah, that's a good question. It's a hard question to really answer from just an efficacy standpoint because it's really going to depend on they're looking at different materials for heat sinks for better thermal resistance, possibly different configurations. Do I add active airflow to the system to be able to keep that heat down? So there probably are ways to do it right now with the efficacy we're at. It's just it may raise the cost too high for the typical residential market, which is probably the greatest opportunity in the retrofit to actually go out and buy. So I'd say you're probably there and can do it now. It's just the design of that system is going to be probably pretty costly. So from an efficacy standpoint, where does that need to be? I can't really answer that at this point in time. It's really kind of in the end customer's hands, looking at what they can do, how they can do it, figuring out a way to keep the cost down.
Okay, I think we'll end on one forward-looking. Well, I guess what I just asked you was forward-looking, but here's a little more forward-looking. What improvements do you see coming soon to market in bringing up CRI for all illumination class LEDs from kind of the current standard of 75 to 80 CRI? I guess is it only a matter of time before everybody has 90 in every product line, or what do you see in terms of color rendering, the quality of the color?
Yeah, I mean, that's a good question. I don't know if everybody's watched the CEC, but they've just put out a new spec for 90 CRI systems. I mean, you can do 90 CRI in most LEDs. It's just really it's kind of a change of the phosphor. The drawback there is you're going to get a reduced efficacy in the system. So I think depending on what the customers are requesting, it's really going to be dependent on the opportunities and what our customers, the people out there buying the systems, are wanting to see. It's going to drive 90 CRI in all LEDs. But I don't think the opportunity has hit that point yet to drive everybody to the 90 CRI.
That's a good point.
And do you really need 90 CRI? I mean, that's another question.
Yeah,
you really need it?
I think you're exactly right there. I think the applications are what's going to matter, and the application should dictate things like overdriving LEDs and how that impacts lifetime, right?
Right. Yeah, exactly.
Okay, well, very good, Doug. I appreciate the time you took answering those questions. I'm afraid we're out of time today. On behalf of LEDs Magazine and Pinwell Corporation, I'd like to thank Doug for a great presentation, and thanks again to Seoul Semiconductor and to Digi-Key for sponsoring today's presentation.